you have two set of fractures developed in the rock with different orientations, and the rock, it's under stress, and it's given the sigma 1 is horizontal, and sigma 3 in that case it's going to be vertical. And here it says, okay, the confining pressure is equal to lithostatic load. So the confining stress or confining pressure indeed is sigma 3, right? So here, sigma 1, we know sigma 1, it's horizontal, right? And sigma 3 is lithostatic pressure. So indeed it's vertical, right? Here it's giving information that the sigma 3 is vertical. And then in terms of the the value of sigma 1 and sigma 3, it's unknown. We should actually find it, and there's a table that's giving some information. So it gives the density, that's fine. It gives the cohesion, it's a 50 megapascal, and it gives the two coefficient values, one for internal friction and one for sliding friction. So this one, okay, if we are dealing with the bulk rock, okay, if we are dealing with the bulk rock, so you're gonna use the internal friction angle, right, or coefficient of internal friction. But if you are dealing with the fractured rock, let me put that one with another color. If we are dealing with the fractured rock, okay, you are going to use the coefficient of sliding friction, because now your rock is it's fractured into at least in two blocks, and block 1 is going to slide on top of block 2. So keep in mind what's the difference between these two. And mu I, it says indeed it's a I stands for internal, and S for mu S stands for sliding. So how you actually put these three numbers in the graph? I'm going to draw my sigma n and sigma y, sigma n and sigma s axes, and as you know, we can draw our internal friction angle, something like that. And here, this value is going to be 50, right? This is 50, and this value is given as a cohesion. It's S0, right? And this angle, we don't know what it is, but we know the cohesion, the coefficient of the internal friction. We know the mu, which is 0.51. If you get the arctangent of 51, it's going to give you the phi angle, right? So we use the coefficient of internal friction to draw, this column failure. And if we are dealing with the sliding friction, in that case, there is no cohesion, right? So in this situation, okay, the S0 is equal 0. So in that case, you should start from the origin, and you use arctangent of 8.85, and you find the angle, and that's gonna be okay phi for sliding friction. So this is one point you should remember. You're starting from the origin if we are dealing with the fractured rock. So let's go ahead and see what is the question is asking. Okay, part A is asking a maximum possible magnitude of sigma 1 that the rock can support at 1500 meter depths. So since it's just talking about the rock, right, it doesn't say about any kind of fractures. In that case, you are going to use indeed internal friction angle. So again, let me draw my graph, and from there we see how we gonna process this. This is sigma n, this is sigma s, and I know I should deal with the with the internal friction angle, and here I will write, mu is equal 0.51, and I know the phi angle, or let's say phi is equal arc tangent mu, right? And it's again the same thing that we did for mu, right? The mu is equal tangent phi. If you want to calculate the tangent, you take the arctangent from both sides, then the arctangent and tangent will cancel each other in the right side of the equation, and you left with the arctangent of mu. So if we calculate this, the arctangent of arctangent of 0.51, it's going to be equal to, let me calculate this. So you can use your calculator for sure. If you want, you can do it with me, and make sure your calculator is set for degrees. So arctangent of 0.51, it's 27.02. So I'm going to simplify that one and put 27 degrees, right? So the phi indeed is 27 degrees. So how you can manage this? You count along sigma s, 50 megapascal, right? You scale that one and you find the 50, and from 50 you use protractor to draw a line with the angle of 27 degrees. Okay, so again, my drawing is not perfect because I don't have my protractor. And next we are going to calculate the sigma 3 and sigma 1. Both of them somehow are not given, so we should find a way how we should calculate those, right? So as you as you go through the problem, you see, the depth is given, the density is given, so you are able to calculate the confining stress by using these numbers. What that means, it means you can calculate the sigma 3 with the given data, and sigma 1 is indeed is the one that we should find out. For finding a sigma 1, again, there is two ways. One, doing graphically. It's going to give you the answer, but based on the scales that you're choosing and the quality of the tools that you are using, you might end up to different answers. It's not going to be that much of large changes from one to the other, but it's going to be some kind of changes. I will do it in graphically, and also I will do with the functions in both way, and you will see how we can go through this. So I'm going to clean up this and redraw the things one more time, because we know now, okay, we know this angle is 27, we calculated that one, and we know the value of this portion, or the cohesion, is 50 megapascal. So I need to find my sigma 3, right? And let's say how we're gonna do that. So let me do in different colors. Sigma is equal force applied to unit area, right? And we know when we say unit area, indeed 1 meter by 1 meter, or 1 square meter. So here it's going to be 1, and at this situation, sigma is going to be equal F. So if I calculate the amount of force applied, okay, by 1500 meter of the rock thickness, in that case, I can actually find out my stress, which is sigma 3 here. So we know sigma is equal F, and we know F, or force, is equal mass multiplied by gravity, right? So if you find the mass and you multiply with the gravity, it's going to give you the amount of force, and since this force is applied on area equal 1 square meter, in that case you are getting a sigma value. So from here, again, the mass, indeed, the mass is not given. The only things that we have is the density, and we have the dimension. So the mass indeed is volume, okay, multiply with density. You can plug these two values into the first function, and then you can get the F. So F equal mass multiplied by gravity indeed is equal volume multiplied with density multiplied by gravity, right? It's the same thing. So we have the volume, right? The volume indeed is 1500 meter in the z direction, multiplied by 1 in the x direction, multiplied by 1 in a x dimension. So this is a column of rock, and the volume of rock is 1 meter by 1 meter by 1500 meter. Okay, it's something like, let's assume that's the column of rock, and here in the depth dimension it's 1500, and here it's 1, and here it's 1. So if you multiply this with the density, you're gonna indeed calculate the weight or the mass. So we know this 1500. Here the volume is square meter, right? Square meter multiplied by another meter, it's going to be cubic meter. And therefore, if when you are plugging the density, you should actually keep the same units. So as you see here, the unit is provided in kilogram per meter. Indeed, the unit, it seems it's quite it's not quite right, because kilometer, it's going to be kilogram per cubic meter. So that needs to be fixed, but in terms of the number, we are fine. We can plug 2720 here, right? Multiplied by the G value, it's 9.7, right? It's the gravity, and you can plug 9.7 here. So if I come up with this number, that's gonna be my force, right? And I know the force is equal to stress. So let's do this calculation, and we find what is the value of sigma 3 here. Let me do this calculation. I will multiply 1500 by 2720 multiplied by 9.8, and the value is going to be 39,984, okay, 000. And the unit for this, right? So we know this is the first part, it was cubic meter. The second part indeed is kilogram over squared cubic meter, and the gravity is over it's meter per squared second, right? These are the units. So if I multiply these three units, this m3, it's m power 3, it's going to cancel this, and you're going to end up to kilogram, okay, meter per squared second, right? And this unit indeed is Pascal. So I need I need a megapascal for this, or you can think I have a large number like that, so how I can simplify this. If you divide this value by 1000, okay, it's going to give you kilopascal, and if you divide by another 1000, it's going to give you, okay, megapascal. So here my answer, it's going to be 39.98 megapascal, right? And why I calculate megapascal? Because these value, okay, the cohesion, it's given in megapascal. So that's why I am doing in this way. So now we know the sigma 3, right? Because we are calculating in depth, and we know the sigma 3, it's vertical. So here indeed the sigma value indeed is sigma 3, and you can choose your sigma here based on the scale that you have, and let's say this is about 40 megapascal, right? I'm just writing in, I'm making a little bit simplification here. The 39.98 we can take as a 40 megapascal. So now we have everything indeed to answer the part one. How? I have my sigma 3, I have the Coulomb failure, and what I need to fit a circle here that touches or touches the tangent line. So you can increase to this situation, and here, okay, indeed you are at the boundary of stable or broken, right, zone. In that case, your rock, it's going to hold the maximum stress as this one for sigma 1, right? So if you are doing graphically, you can try to fit a circle here, and that's, you should try a few times to indeed to increase the size of the circle that is limited under your failure envelope. So this is like, this is the way of doing it graphically, but we can do also, using the functions that last time we went through it, right? Give me a few seconds. I will go through the, if you want to make a note, you have 1 minute or 2 minutes, make your notes, and then I will go through the functions, how you can indeed calculate this using functions we discussed last week. I think you guys, what you can do, if you right click on the view, or on in the white page or on my slide, it's going to give you an option, save the screen. It's going to actually make a snapshot of this, and you can keep the record in your computer, and when you have time, or if you need as a picture, then you have everything in one place. However, we are recording this as well, so I'm going to remove everything here. We know from here that our sigma 3 is, let's put exact number, 39.98. Okay, so I know my sigma 3 was 39.98 megapascal. And I am going to find out what is the maximum sigma 1, right? So from last, we know there's a function between sigma 1 and sigma 3. If you remember, we said sigma 1 is equal to strength of the rock under compressional force, right, plus K sigma 3, right? So, and this function, sigma 1, is unknown. Strength of the rock under compressional force, it's unknown. The only thing that is given, indeed, is the cohesion of the rock, or strength of the rock under shearing force. But we know that there is a function between the strength of the rock under compressional force and strength of the rock under shearing force, and that is indeed is equal to multiplied by shearing. Indeed is the strength of the rock under shear force multiplied by square root of K, and we know K is equal 1 plus sine phi divided by minus sine phi. Okay, we plug the numbers here, we can actually find, we have the phi, right? The phi, we calculated phi, it was 27 degrees. So if you plug phi, you can find out K. So we have strength of the rocks under shearing stress, which is given here, right? Either S0 or S, as its strength of the rock under shearing force. So they use different, pattern for that. But if you plug these two numbers, you can find the strength of the rock under compressional force, and then everything is known, and you can find sigma 1. So you can work on this, and I'm gonna work by my own, and we can check the answers together. Okay, give me a few minutes, I will do that, and you can do by your own as well. I'm going to calculate the sine phi, which is equal 1 plus 0.45 for 1 minus Okay, here I have the K. For me, it's 2.66. So if I take that one and plug it here, so I have 2 multiplied by 50. Okay, it's given, multiplied by square root of 266. And this is equal to 163.9. Okay, and the K has no unit. Okay, it's unit free because it's just the ratio, right? And SC indeed is the strength of the rock under compressional force, and this is megapascal, right? And then what you do, you plug it here. Now this value is 163, okay, 0.09 plus 266 multiplied by 39.98. So if you calculate this, you will come up with the sigma 1 value. So let me do that. 39.98 multiplied by 266 plus 163.9, and the value is 269.44 megapascal. Okay, so this value now is sigma 1. Let me see the questions. It seems there are a few questions, and then in the meantime, if you have yes, the unit of the density, it's kilogram per cubic meter. or kilogram multiplied by m power minus 3, as you said. Yes. All right, so we got, sigma 1 value for both graphically. Yes, yeah, I mentioned there's a typo in the density, in the table for density. It's not 2720 kilogram multiplied by m power minus 1. Indeed, this is this unit. Let me clean up this. If you want to take the screenshot, take it, and I will raise it in a few seconds. Yeah, this is wrong. Okay, it's indeed 2720 kilogram per cubic meter, or you can say kilogram and power minus 3. Okay, you can change that minus 1 to minus 3. Let's move on to the B. So it says, okay, it says if the orientation of sigma 1, it's it's 130, and there is two set of fractures that it's giving, it's given. It is asking, is there an option of moving on the on which one of these fractures. So if I go to the title of the questions, right here we see there is a vertical fractures with the strike of 3, 40 and 15, and we know, for instance, what you can say, you say this is north, and I have one set, okay, fractures like that which has an angle of 15 with north, and you call that F1, and there's a second set, it goes, okay, 340 as F2, right? So if this is north, okay, this angle is 15 and this angle is 340, right? It's the azimuth. So you have two set of fractures, and the question is asking if the sigma 1, okay, if the sigma 1 is 130, if the sigma 1 orientation is like that, which one of them is going to be activated. So let's go to here. We know we have two set of a fracture. Let's say this is north, and we have one set of fractures. Azimuth is 15. Okay, I call this one F1, and the other one indeed is 340, and I call this one as a F2. And we know the sigma 1, it is with respect to the north, it's 130. Okay, so let me put some kind of dash line here, and let's say this is 15, and if this is, again, if this is north, this angle is 130, and this angle is 340. I hope this is clear. You guys know why I'm doing it that way. So what I'm gonna do, I will find out which one of these two, okay, will be activated. So what you're gonna do, again, the easy way, you draw your Mohr circle. So this is sorry, this is shear stress, not sigma 3, and this one is normal stress, and this time we're gonna indeed include the confining, we're gonna include the coefficient of the sliding friction. So if you take the arctangent of 0.85, okay, arctangent of 0.85 is equal to, that's going to give me the angle of the phi for the Coulomb failure. Let me calculate this. Arc tangent of 0.85, it's going to be 40.3, okay, 36 degrees. So you take your protractor and you put it, at the origin, and you draw a line like this, and the angle of this line, it's going to be 40 point, okay, let's say 3 degrees. Okay, so now I have my failure envelope, right? Let's keep that one that way, and I know the sigma 3 is 40 megapascal, right? We calculated that one from the previous example, and since we know we know now that we are looking to the fractures, then we need less sigma 1, right, to break the rock. Because if I show the other Coulomb failure here that we had, right, I can actually fit a larger circle, right, with the same sigma 3. Let's do it that way. With the same sigma 3, I can fit a larger circle to compare with the sliding friction, which I'm able to fit a smaller circle, right? Because as soon as this blue circle touches the blue failure line, one of these fractures will be activated, right? Yes, the question answer is yes. There is a maximum stress, will be reached, and one of them will be activated. Why? Because under these circumstances, under sliding friction, right, you need smaller sigma 1 to compare with the bulk rock, which needed about 260 megapascal, right? So the condition is yes, and which one of these two set of fractures will be activated? We should find that one. How you do that? We know that we need theta angle, right? And we know theta angle is the angle between fractures and sigma 3, right? And I know sigma 3 here, it's perpendicular to sigma 1. So if this is 90, the remaining angle here, okay, it's going to be 40 degrees, right? The sigma 3, it's making an angle with north about 40 degrees. So if I subtract this 40 with 15, it's going to give me the angle between fracture or F1 and sigma 3, and that angle indeed is 25 degrees, right? So if I multiply, or I can write here theta for F1, okay, it's 25 degrees. So here I need to plot it here. So if I multiply 25, it's going to be 50, right, for theta F1. And for sure, as you see here, this point, it doesn't cross my failure envelope. In that case, this is not going to be activated. So let's look at to the other one. So we need to find the theta of F2, and we know from the north you have 20 degrees counterclockwise and 40 degrees clockwise, which shows to us the angle between sigma 3 and the failure plane, which is 60, right? So I put 60 here. If I multiply by 2, it's going to be 120, and you will see here, okay, this is crossing or it's reaching to the failure envelope under, sliding friction. In that case, one of these sets is going to be activated, and that one indeed is the one that is oriented 340 degrees with respect to north. So this is going to be, this is going to cause here, this is going to be, this is fixed. It's not going to have any movement for F1. and F2, okay, F2, it's gonna have some movement on it. All right, so by saying that, we are at the end of this